So I'm Andrea Barisani. This is my colleague Daniele Bianco, and wave to the audience. Wave to the audience. Be nice. Wave. Wave. Okay.
Hi to everyone.
So we will talk about some very exotic and old school but interesting topic to us, which is really pushing the limits of what you can do with Ethernet packets, which, you will see. It's really interesting. So before starting, we want to dedicate this talk to our friend Barnaby, which tragically passed away. So I know that at the keynote they did a moment of silence for Barnaby, but if you knew Barnaby, you would know that he would have been preferred to cheer up. So please give an applause to Barnaby Jack. Thank you. So our talk is about expanding and pushing the limits of what you can do while testing Ethernet connected device. And the reason why we found this topic really interesting is that it is generally assumed that you can send and sniff arbitrary packets using a normal laptop. And this is actually, turns out not to be true. And you know where a hacker cannot send completely 100% arbitrary packets, you have that, that weird itch that you need to scratch, that you need to fix somehow. And while testing some specific classes of embedded devices, all this research and this work, felt natural. Because the problem is that when we're talking about Ethernet packet, there are some values like the frame check sequence or the start of frame delimiter, which historically require the use of dedicated and very costly hardware to manipulate. So in this presentation, we will dissect how Ethernet works at its very lowest level, and we will present some novel techniques for testing and attacking certain kind of systems. And we will release some code and some hardware for doing this. So what are we talking about? So you might all be familiar with an Ethernet frame. What you might not know is that every Ethernet frame that you send on the actual wire has fields such as the start of stream delimiter that we see here, a preamble, and a start of frame delimiter, which generally you don't get to play with. These fields are used by the network interface card to detect the actual beginning of the frame in a reliable way, because otherwise you cannot just do that by relying on the payload of the packet. And in every Ethernet you have two components. Like from a hardware perspective, you have a PHY, so a chip which handles the physical layer of Ethernet, and then you have a MAC, which is what handles the inner layer. So the PHY, the physical chip, handles the interframe gaps, so the idle part here, the start of stream delimiter, and that's it. So, and these fields are not, and the end of stream delimiter, sorry, which tells the network interface card when the frame ends. And these fields are not available at the MAC layer, so you cannot play with them unless you emulate a PHY, which is the physical chip. Now, what we target are actually these other fields here, the preamble and the start of frame delimiter, which are available to the MAC, but they're not available at the driver layer. So these are fields that you cannot manipulate with a normal laptop. And then after the start of frame delimiter, you have the actual frame which you can manipulate freely with the destination MAC, the source MAC, the ether type or length, depending on the packet that you're trying to send, and then the actual payload of the packet. At the very end of the packet, you have the checksum for Ethernet frame, which is the frame check sequence, which is 4 octets. So because of this separation between the PHY and the MAC, so there are several things that go on here. There's a need for having the PHY signaling data. So with PHY signaling data, we refer to the start of stream delimiter and the end of stream delimiter to be unambiguously encapsulated in relation to the MAC frame. This means that whatever the MAC is doing, the MAC cannot inject those symbols into the frame. Okay? So the encoding of of the symbols in the frame, they need to be done in a way that the Mac cannot possibly inject those, so that you cannot have an in-band signaling from the Mac layer. Like, think about it like when you have in-band signaling for, phones that you can play the MTF tones. If those would be signaling codes for the line, then you would have a problem. So there's the need for having a separation there. The Mac signaling codes, like the preamble and the starter frame delimiter, are, however, represented with the same symbol which are allowed within the Mac frame. So, and here you have this distinction between what the physical layer stream handles, so what it sends. This is called the Mac packet. This is the packet that is sent by the Mac to the PHY. And this is the Mac frame, which is what your driver on your operating system sends to the Mac. So these are the three layers which are involved. So the way the signaling codes are transmitted, there's something called the 4-bit to 5-bit encoding. And this is done specifically, is done for many reasons, but also to prevent, to add additional signaling symbols that you cannot send within the payload of the packet. So we can see that 4 bits are actually encoded using 5 bits, and that we have additional symbols that are not part of the standard hexadecimal values that you can put in a Mac frame. So we have from 0 to F, we have those symbols, and then we have additional symbols I, J, K, T, R, and H, which are the actually signaling codes which are used within the packet. So, interesting fact, actually when you talk about Ethernet 100 megabit per second, this transmission rate means that the actual bit rate of the data which is being sent is 125 megabit per second, because you have this overhead in the 4 bits which are translated to 5 bits for this specific reason. So we have 16 data symbols and 6 signaling symbols. So again, starter frame delimiter is not available at the US driver layer, or not even if you modify the firmware of your network interface card. Some people think, oh, you have the firmware, you modify it, you modify the driver, you can play with that. No, you cannot. That is being injected by the Mac, so unless you are a Mac, unless you are the Mac chip, then it is not going to work. The frame check sequence, which is the checksum, is generally not included in the packets handled by the operating system, as usually its check or computation is offloaded by the Mac. The Mac automatically does it to save, some CPU cycles to the US. Other challenge, usually packets which have an invalid checksum are discarded by the Mac, so you will never ever see them because they're never sent to the US. So the motivation to do this kind of research is that, again, when you have something that you cannot manipulate in packets, it's really annoying for people that do security. You want to be able to control 100% your attack surface to trigger, unexpected behavior that might have security implications. And there are many devices in our line of work. We work a lot with automotive, industrial equipment, avionics, lots of embedded system, and in many cases, these embedded systems, they only have a PHY, a physical PHY chip, and the Mac is actually implemented by software. So you have a software Mac implemented on the FPGA, so it's not something which is, made in silicon and hard-coded there. And also you have a certain class of devices which are Ethernet multiplexers, which are appealing targets because they use Ethernet frames in a very arbitrary way. They defy the normal formats of the frame by using stock Ethernet hardware at the same time. And this work was motivated by testing these devices. So the first challenge, it's easy. Receive invalid packets and frames with invalid frame check sequence, because your frames, you might be talking to devices where they don't have a frame check sequence, they actually use that as a data, and you want to receive that. So easy thing to do, most Ethernet drivers, you can use ATH tool to tell the interface to actually receive the frame check sequence and receive every packet. So we see in this example here, this is a normal Ethernet frame received. So we see that the payload ends with the last bytes of the actual payload of the packet. If you receive the packet with the frame check sequence, you have these additional 4 bytes which actually represent the checksum of the frame. When using RxFCS on in combination with RxHold, you also receive packets which have invalid frame check sequence. So you basically receive everything that comes on the line. So this is easy. You don't need any patching. Now, if you want to send packets with an arbitrary frame check sequence because you want to talk to the same systems that they use the FCS in a different way, then usually your network interface card does not allow you to do that because it computes the frame check sequence on its own. So you need to patch the kernel. The easy way, you read the datasheet for the Mac that you have and the PHY that you have, or you dig into the source code, and this is a way that you can patch easily the kernel for injecting arbitrary frames. So this gives you a little bit of freedom in controlling the last 4 bytes of the payload, which usually you cannot control. But this is not enough. Anyway, this is an example. So we send a packet with and without the FCS injection patch. We can see this is the receiving side. We can see that in the first case, with the patch, we get a packet. So we can see that these bytes, 27, 1, 2, 32, A, B, are not received, which means that they were actually parsed as checksum by the Ethernet. So this is a computer which is receiving the packets without any patch, so the frame check sequence is not shown. If we send this same packet without a patch, we see that these bytes get to be part of the payload. So they're actually not being used as a frame check sequence. So this is different. This shows that you can control those values. So, but anyway, this is not enough. This is not too interesting. So we want to manipulate the preamble and the starter frame delimiter values. So we want to be a Mac. And usually you would need a very expensive network analyzer. We're talking about, $4,000, $8,000 US dollars, or, the way to do it on the chip is to use a dedicated hardware setup. So usually you have an FPGA or a sufficiently powerful microcontroller that actually will implement a software Mac, and you wire that to a PHY. So we have identified a very low cost solution, which is called the XMOS XC2 Ethernet kit, just to proof of concept that you can do it on the chip. This costs, it's very cheap right now. It costs, I think, $80, And it is a platform which has an embedded processor attached directly to a PHY. So whatever firmware you put on this simple device, you can be the Mac, and you can control the fields that we're talking about. So this is the hardware. It's off the shelf, and we developed custom firmware for it, which we're going to release today. So we have this custom injector firmware, which allows you to arbitrarily send your packets. So we can see in this case, we have the preamble. So the preamble here is 5555. This is standard preamble. So you have these 7 octets of 55. Then you have the starter frame delimiter, which is D5. Then you have the actual payload of the packet, which begins with the destination MAC, source MAC, and so on. And then at the end, you have the checksum. So this is the maximum injection that you can do by being a Mac. This is controlling 100% of the frame, excluding the PHY signaling codes, which anyway are not that interesting to us. So, and this firmware will be released, today. So now the question is, what can we do with this? So the first interesting thing that can be done, you can fingerprint network interface cards. So suppose you have an embedded device, you do black box texting, you don't know, how the software works, how the software Mac works, so you want to understand, what kind of system it is. Because there are ambiguities in the way that Ethernet packets are parsed at the Mac layer, you can fingerprint the different systems. So we see here that, for instance, Intel cards, you can have, so the first byte can be anything. This is always the case because the first byte gets converted to the start of stream delimiter by the PHY. And then you need to have the standard compliant preamble, which is made of 55, but it doesn't have to be of the actual standard length. It could be of any length. So this should be 6 octets, but it can be of 1 octet. And then you need to have the compliant standard frame delimiter, which is D5. But there are other Macs where you can actually, you're not required to have your compliant preamble. It can be any bytes. And in some cases, you're not even required to have the compliant starter frame delimiter. So you just need a nibble in the starter frame delimiter to be compliant. So you can have D1, D2, D4, and the Ethernet will receive the packet happily. So these differences in the way the MAC handles packet allow you on the same LAN to fingerprint the different MAC implementations, when you're directly connected to them. And this also raises, an interesting attack, which is evading passing network taps. So this is a tap, this is a Ninja throwing star LAN tap made by Michael Osman. Is Michael here? Michael, are you around? There. So Michael is a very evil man. He's an evil ninja that goes around with his, cute passive taps, showing how cool they are. So since Michael is evil and we hate him so much, he's such an obnoxious person, we want to evade his cute little toys. So the way you can do it, you can exploit these ambiguities in handling packets so that you can send a packet that the tap will not see and that your final target will see. So in this case, these packets will be happily received by a Cisco Catalyst 2950 because it is very loose in checking the starter frame delimiter byte. But if you have an Intel-based network interface card listening on the tap, it would silently discard it. So you can have a communication to your target LAN, and whatever IDS is attached to the passive tap, it will never see any packets without even notifying the OS because it will discard them right away. And this is, this is one example of doing. So we see that we have a standard preamble 55555, and then we have D1 instead of D5, and this works in this specific scenario. And by mapping all the possible fingerprints that you can have, you can play with this kind of situation and defeat the evil ninja throwing passive tap that Michael made. So Michael, you've been defeated. Good. So now there are also other interesting conditions. There are some parsing anomalies in parsing the starter frame delimiters. So let's examine this packet that now we can send with our own hardware, and we're actually also going to demo this in a second. So this packet is peculiar for many reasons. So first of all, we have a preamble, 1 byte, because we see in the preamble it doesn't matter how long it is, and we have a starter frame delimiter which is not compliant, D4 instead of D5. Then we have the destination and source MAC address, we have the ether type, IPv4 payload. Then we have another preamble and starter frame delimiter within the payload of the packet. We have another destination and source MAC address, and then we have payload, and then we have the frame check sequence. Now, the checksum of this packet is calculated in a way that if you would consider this Ethernet frame from the offset 0 to the N, or if you would consider this frame from offset 1D to the N, the checksum is the same. So we're exploiting a CRC 32 collision, which is trivial to generate. So the checksum for this packet is valid at 2 different alignments. And these 2 different alignments, they both represent a valid Ethernet packet with destination and source MAC addresses and the payload. So we have a packet-in-packet situation, a frame which is nested into a different one. So normally, whatever you put in the payload of the outer packet, it's just a payload that you put in the packet. No signaling codes will be allowed there. So there are certain class of devices, like for instance the Marvell 88E6060 embedded switches, which is present on many devices. We have one here, which is TP-Link router, where this has unusual behaviors. So you have something called the Schrodinger's packet in this case, as we like to call it. So when you send this packet, it doesn't matter the speed, the rate for sending the packet. It will get randomly aligned at different offsets. So you might get that in 4 cases it's aligned at 0, 0, in the whole packet, or the other 6 cases it's aligned at 1D, and this happens randomly. So let's try to demo this. So now I am connected to the TP-Link, and this other computer is sniffing directly on So let's try this on the switch. So okay, there we are. So we are connected with the XMOS. This is the XMOS, which is connected. We connect it to the switch. So I will, and on the other hand, we will sniff the packets that are coming on the Ethernet. So not SSH though, because that's not good. Okay. So I'm connected to the XMOS here. Okay. Now we're firing up our injector. Woo! Demo. Fail. Problem connected to device. Okay. Okay. Can you unplug it and replug it, please? I told you she was not a virgin.
Yeah. I'm not that good in recognizing virgins. You know.
Device disconnected. Ah, yes, maybe if we power it up, maybe that will be helpful if we attach the power to it. That's usually a problem. Thank you. Noobs. We're noobs. Give me power.
Here we go.
Okay, it's blinking. Blinking is good. We like things blinking.
Try on. No, not.
Okay, so now I can enter arbitrary payload. So we have the cat box here. Now, so here, where is it? Here I'm sniffing, and now I will send this packet 10 times. Okay. Now, oh, are you attached to the switch? No, you're not.
No, aspetta. No, come. No, scusa.
You have one thing to do, and
You did that. It's not my fault.
okay. So now,
giusto. C'ero già, no?
okay. So now let's replug that. Bear with me for a sec.
Aspetta, cosa?
Devo riattaccarmi qua.
Tu sei questo. Tu sei
No, tu scusa, tu. Okay. So now what happened here? So this is the dump of the packet that we sent. So we can see that in some cases we have a dead kitten. Here we see that the kitten dies. This is why I call the Schrödinger packet. And in this other case, the kitten survived. So we see that we either have a TCP SYN or we have a packet which, you know, is aligned to a different one. So if you check closely, this packet here actually matches the packet which is aligned from this offset here. And I've sent the same packet 20 times. So this switch is randomly aligning the detection of the packet at one of the two offsets. And depending on the offset that we're aligned to, we either have a dead kitten or a live kitten, okay? So it should be a cat, but we like a kitten because it's much more, you know, gruesome. So it's better, right? So this shows how this device, for instance, has a race condition in parsing the starter frame delimiter, because remember, we're not using a compliant starter frame delimiter here, we're using something which is not compliant. And it creates issues on this specific hardware. Now, the interesting thing is that depending on where the race condition is, if it's depending on where it is in the circuitry, it might happen before or after some check-in, such as VLAN tags checking or some routing decisions. So it's an interesting class of problems to probe, because this might affect some security-related decisions that you might have. So this was one of the first things that we found, and we thought this is interesting, we should investigate this more. And it provides a case for actually manipulating 100% of the frame, because you can trigger a certain specific condition. With FPGAs, with softmax implemented in FPGAs, you can often trigger the null of service condition. You can put the state machine in the FPGA in a state that would cause an infinite loop, because it would expect a certain length, because they read the standard and they implement the standard. But if you defy those expectations, you might trigger some improper state in the state machine, and with one packet you could just shut down the Ethernet receiver forever. So there is a case for actually manipulating these frames, other than killing cats, like in this case. So, and this is the example in the presentation of the two aligned packets. So we see here, this is the actual other starter frame delimiter and preamble. And we can see that the checksum is the same for both packets, and both packets are valid and both packets are detected. Now, packet in packet on wire Ethernet. So what this led into exploring is the injection of raw frames at layer 1, which is something that has been explored by Travis Goodspeed for wireless frames in stuff like Zigbee and so on, exploiting the signal degradation which is characteristic of wireless signals. Now, the same kind of injection would be extremely appealing for Ethernet frames. But the problem is that Ethernet is very reliable, so you cannot just wait for a random bit to flip and allow you to inject your packet in packet, because the first starter frame delimiter is missed for whatever reason. So we explored the possible condition that would allow us successful packet in packet injection on Ethernet frames. And there are slim, but there are reliable scenarios where you can actually do it, and it has actual, an impact on certain class of devices. And it turns out that it's a design flaw. It's not an implementation flaw. So we talk about the PHY and the MAC and the way they're connected together. So when a packet is being sent, the MAC, there are some lines which give the data to the PHY. So in this specific case, this is a standard MII interface. You have you send 4 bytes at the time, and then you have the clock, which is sent by the PHY to the MAC, and you have a transmit enable line, which basically tells the PHY when this valid data to present to the PHY. Yes, 4 bits at a time. Yeah, I sent it. Yeah. Thank you, Daniele, for your contribution. So now there's a problem in this approach. So if we create a condition where the PHY is either starting up, or the PHY loses the link, or it's in a state where it's not sending packet, the problem is that the MAC doesn't know. He has no knowledge of that. So when the MAC is sending packets to the PHY, if the PHY is in a condition where you cannot send the packet and at some point it resumes that function, packets have a chance of being detected in flight by the PHY. So you're sending a long packet, and if you can trigger a reboot or a startup of the device, a link speed change, or you're simply replugging the cable, the PHY has a very high probability, if you craft your packet in a special way, of receiving this packet like, halfway through. Now, since the preamble and the starter frame delimiter are encoded in the same fashion as the payload of the packet, they're not like the PHY signaling codes where they use symbols that you could never possibly transmit because there are symbols that are simply not available to you because it's out of band for the MAC layer. In this case, the first valid preamble and starter frame delimiter, which are witnessed on the wire, will be detected and parsed as such. So if your packet is being detected in flight, the first bytes which matches with those values will represent the starting of a valid packet for the flight. And this, on the other hand, does not require, so it was explored with dedicated hardware, but at the end it actually does not require any dedicated hardware. It can be accomplished with both local and routed packets. There are a few things that needs to be taken care of. So this is the example. So we send a packet that has, with these values we don't control. Suppose we send it remotely from the internet. So we know that the final packet at some point in his long journey to our destination will go on Ethernet and will have a standard starter frame delimiter. Now, we put our data, we put another starter frame delimiter here, additional data, and we need to make sure that the final packet that is being transmitted at the point of exploitation has a frame check sequence which is identical, like in the previous case, for the two aligned packets. And also, one thing that we do, we put a lot of padding between the beginning of the legitimate packet and its header and the injected starter frame delimiter, because when the packet is being detected mid-flight, the more distance we have between the original starter frame delimiter and the one which is ejected inside, so the more padding we have, the higher the chances are that the packet is going to be parsed in flight in the padding area. So if we maximize those chances, we maximize chances of the second starter frame delimiter, which is within the payload, of being detected. So in this case here, in this packet here, we have the original header. Then at some point we have 4 bytes that we need for creating the CRC32 collisions. Then we have a full preamble, a starter frame delimiter, and then an additional packet that goes on here. Now, since this packet is routed, we need to anticipate for the routing modifications, but that's not, for the most part, is not difficult to do, because the time to live is something that you can probe. You can try to guess what the time to live is going to be. The IP checksum, which is modified, because the time to live is modified, you can change right away. The real problem here are the source and destination MAC at the point of injection. Either you need to know them, you need to guess them, or you need to attack a layer 2 protocol where it's either using predefined source and destination MACs, or on IPv6 actually you can infer the MACs in certain scenarios from the actual IP addresses that you're using, because the IP address, the IPv6 address is derived from the MAC. And this is required for doing the CRC32 collision. So we use Julian Tin's CRC32 collision helper tool, which is excellent. So we've wrapped it in a script which allows to conveniently do the modification on our payload. This is also going to be released. So in this specific case, we use a UDP packet because, so John Postel teaches us that in UDP packets you can disable the checksum. You can put a checksum 0, and then you don't care about tweaking the UDP checksum when you do your compensation. This is actually not required. It is convenient, but it's not required. Even if you're targeting a protocol which has internal checksum, it is not going to be a problem, because you can always craft it in a way that the checksum nullifies itself at some point, and then you can have your own injection. It takes a while to explain, but it can be done. And email us if you want more detail about it. And again, the real issue here that makes it not super practical is the fact that you need to know the source and destination MAC. Unless you're dealing with a protocol or systems where those addresses are known, or you're dealing with IPv6 where you're using EUI 64 addresses derived from the MAC address. So let us do a demo of this. Okay, so what we're going to do, this laptop here, which is injecting the packets, is connected to a router, which is connected to another router, which is connected to a switch, which is connected to the final destination. So we're routing the packet through multiple devices and multiple switches to show that we're not doing this locally. So did you check that the connections are good? Is it going to work? Okay. So we're not using the XMOS here for doing this. We're just using a standard packet which is being sent over the wire. So this is what we're going to do. We're going to have, okay, we can kill this. It's not.
It's going to work in just fine. I'm sure that she was a virgin.
We have time. We'll do it live. So here I'm going to sniff for packets on port, from packet on port, wait a second. Your shell skills and system administration skills, they nullify themselves when you're presenting in front of an audience. You're just like a 2 years old with a console. You don't know what to do when you're presenting. So here, this is the actual, this is the transmission side. We are sniffing for packets on port 666. Here, we will sniff on packet on port 53, also on the transmitting side. So 66 here. And dead screens. Dead. 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 Oh, for fuck's sake. Anyway, okay. So this is the transmitting side. We have port 53 here and port 666 here. So what we were trying to do, we will send a stream of DNS packets, and we want to turn magically that packet invoking science into a TCP packet. Okay? We want to turn that. So on the left side here, you see the transmitting side, and we're sniffing the two different ports to show you that on the transmitting side, we will not cheat and we will not actually send a packet for port 666. We will only send packets, UDP packets, DNS packets. So on the receiving side here, we sniff for port 666. And actually, let me do it that way. Let me suppress the verbose output. And here we sniff on port 53. So on the left-hand side, we have the sending side. On the right-hand side, we have the receiving side. And between these two laptops, we have two routers and a switch. Now, I'm going to do it here. Maybe I have another shell somewhere. I have another terminal here. Okay. Okay, so here, okay. You also forget your password when you're doing live demos. Okay, so okay. So now I'm sending the packet, which is not being received on that side. So wait a second, something is wrong in the connection. So you're attached here on this thing here. This goes to that, that goes to there, and this one goes here. Is your link up? Did you configure your Ethernet here? She was not a virgin, I told you. Don't fail on me now. Okay. È giusto questo.
6610, cos'è 6610? Giusto?
So, yep, it's correct.
Se fai un TCP dump senza niente, quindi solo SSO.
Ti sei collegato a questo? Gli hai fatto la configurazione?
No.
Okay, we know what's wrong. Of course Daniele forgot to do something. Okay, so while he fixes that,
Dov'è? Aspetta, dov'è qua?
just give us a second.
Yeah.
You had one thing to do, and I mean it's unbelievable.
That's not my laptop. I mean, I cannot find anything.
That's a lame excuse.
Where is
it? I mean, okay. Just bear with us. It will be worth it, trust it.
Pensavo che avevamo già fatto prima.
Okay, so let's see if it works now. Okay, so now we see, yes, so now we see port 53. So we have this stream of UDP packets being sent and being received, okay? So now we do the magic trick and we just unplug, you know, a cable somewhere here in the path. Yes, you see that? 666 in the front on the receiving side. And that was not transmitted by his laptop. So this is magic. We turned a UDP packet in a TCP SYN on the receiving side. Now the impact of that is that whatever firewall, whatever filtering you have in between, if you can trigger this condition at a point which is after the filtering, of course nobody will know that that packet has been sent. And the other interesting thing is that packet can be completely arbitrary from a layer 2 perspective. So you can inject VLAN tags, you can inject, you know, MPLS frames, you can manipulate that packet at a very low layer. You can even do the tricks that we discussed about the passive tap, because that packet is going to be aligned at its very beginning of the Ethernet frame. And as you can see, I did one try here. I mean, I didn't have to do it multiple times because the way this packet is constructed is that the padding is long enough to really maximize your chances of being detected in flight. And this will happen with every single Ethernet because this is a design flaw. Basically, it's not an implementation flaw. So every single Ethernet we tested, every single combination works, with a very, very few exceptions that are actually presented in our white paper. So there might be conditions where one Ethernet is very picky about the standard and the other one is very loose. So if you have a non-compliant Ethernet on the transmitting side and a compliant Ethernet on the receiving side, then the padding will be a problem for you. Because it will affect the way the packet is received. But this is a very, very combination. Most of the times, actually the majority of the times that we tested this works. And this was the backup slide. So you can see this request, legitimate request for google.com. It could be a DNS reply, it could be a DNS request, it could be any packet that is going to be routed to the final destination, and it become a TCP packet. And the way the UDP packet works and DNS packet works, in this specific case, the actual payload of the packet in packet does not affect the functionality of the UDP request. The UDP request will be honored by a DNS server. Normally, unless you actively do a TCP dump, you actively dissect the packet, you will not find the trailer data. So it will be a functioning packet. You can nest your packet in packet in a payload without affecting the functionality of the outer packet. And this is very relevant for certain class of embedded systems. So there are lots of systems that we often audit in automotive, avionics, or industrial automation, SCADA systems, where usually you have an untrusted zone that can send data to your device, and this device somehow will rewrap that data to Ethernet packet on trusted networks. Now, in these kind of systems, in our experience, it's always extremely easy to find bugs that would actually reset the entire device because there are many bugs or denial of service conditions. Now, when you hit those, if you can control some data which is going to be wrapped in an Ethernet packet, you can trigger this kind of condition and have your data being sent on a trusted domain. And the other benefit of these systems is that 100% of the times they always use fixed MAC addresses which are documented in the specifications for functional reasons. So we actually had to test this condition in real system, and it would have been a problem with safety impact when the attack is for some reason is not preventable by the way the system it is set up. So you know it is an interesting problem which doesn't have a huge impact on the majority of systems, but where it has an impact, it could be really severe. So we are gonna release today the firmware for the XMOS kit that allows you to send the arbitrary packets. We have a white paper which details everything in a much more complete way than this presentation. We also released the simple patch for injecting arbitrary frame check sequence on your Intel car. We also have the script. And as a future project, we will try to work with Michael Osman here, because despite being evil, he's actually a really nice guy, and he's doing a nice project called Daisho, where he is creating a platform where you can actually man in the middle and either sniff or modify, you know, arbitrary Ethernet frames at a gigabit level. The platform, you know, is more interesting than this. There will be has a daughter board connected with a mezzanine connector, and it will have different kind of protocols and connection that you can play with. But we're interested in Ethernet. We will try to port this work there and to see the applicability on gigabit Ethernet as well as other protocols. Pretty much every time you have this kind of frames which have a marker for the start and the end, you might be affected by these kind of problems. So thank you very much, and now we can take questions. Any questions whatsoever? Yep.
You did the demo by essentially you triggered the conditions and your encapsulated packet effectively be encapsulated by connecting the link and reconnecting, right?
Yes. Can you get a little closer? I cannot hear you very well.
No,
so, or maybe they give you a mic. Yes.
Would the same kind of condition exist if you shut down the ports on the managed switch or managed router, and then the unshut it, unshut?
Yes. So the question is if this condition can be triggered by shutting out a port and turning it back on. Yes. If you change, the speed of the link, if you turn the port down or up, if you reboot the switch, if you plug or unplug a cable, everything that will prevent the PHY because of link state reasons to send packets, when the PHY will come back up, for whatever reason, speed change, all of this condition happens in all of these cases. So the easiest way for us in the demo is to simply plug and unplug the cable. When you want to actively exploit it, it's rebooting the switch or making it crash. Okay? So, but suppose you are in a network and you're targeting a specific system, you just send your stream of packets your entire day, and you might just wait for the server to reboot or the switch for reboot or somebody to plug and unplug the cable, and this will happen with a very, very high reliability. You know, again, we had to try it once. So our success rate with this kind of setup is usually 90%. So 9 times out of 10 we get it the first time. So the demo gods have been kind, so we got it the first time. But it's actually surprisingly reliable in the way it works. And the fastest you're sending and the more padding you put in the packet, the more reliable it will be. But you have 1,500 bytes to play with. So, you know, it's, you have lots of padding that you can put inside. The tricky part is doing the CRC collision because of the source and destination MAC. So in the source and destination MAC, you know 6 octets, like, because 3 for each MAC are vendor. Okay, so you can say, okay, it's going to be Cisco, it's going to be Intel, it's fine. You have those 6 octets that if you don't know them, you might as well brute force the 4 bytes for the CRC32 collision, but that will take a long time. So either you need to know them somehow, or you target a protocol where you don't have this problem with IPv6, or if you have other frames, encapsulated frames. So that's the only tricky part. But for us, in our area of testing embedded system, they always have predictable MAC addresses. It really doesn't matter at all. But that's the only thing that saves this attack from being, a more important problem. But, again, IPv6, this raises the bar for the security of MAC addresses in a way, which often we say, well, no, it doesn't matter if you know them. For this specific attack, it's important, Yes?
Will this work if the packet gets encapsulated on non-Ethernet networks and comes back out?
So it doesn't matter. So you can do it over the internet, we say. It doesn't matter if in the middle you have non-Ethernet. What matters is where you're actually triggering the condition. So you can have all kind of non-Ethernet transport in the middle. At the end, what matters is when it hits your final server or the switch before or the switch before. And you're very likely to have your last mile or so to speak, with at least a number of switches and a number of Ethernet connected. So so it doesn't matter if it gets converted to other transport layers in the middle, because you don't need special hardware for the packet in packet. You're just using your legitimate payload, which so happens to match the symbols used for the original startup frame delimiter. So you just need to wait for any Ethernet link inside, or to control it in a way that the first startup frame delimiter is missed. Yes.
I had a question about virtualization. Have you tried this with an ESX server and a vSwitch or something like that?
Okay. We haven't tried. However, even the virtualization, your host will have actual Ethernet, and since this is not related to the way the driver works, this is a problem between the PHY and the MAC, and it's also a problem on the transmitting side. It's not a problem on the receiving side. So what's at fault here is who's sending the packet to you, not you that you're receiving the packet. And this was actually really hard to debug, okay, to find this, because unless you actually are on the wire between the PHY and the MAC, you don't know who's at fault. But we narrowed this down, and it is the transmitting side. So if your receiving side is virtualized, it doesn't really matter. It will receive the packet because this misalignment is at the injection site. So it doesn't matter if your target is virtualized or not. And even if you have a virtualized router which is sending packet, it still doesn't matter, because at the end of the day you have a physical network interface card with a MAC and a PHY. So it doesn't, the OS layer here and the driver does not play a role in any of this. It is purely between the MAC and the PHY. Any other questions? Good. Thank you very much.